Computer simulation. Computer simulations are used to study the dynamic behavior of objects or systems in response to conditions that is not easy or safely applied in real life. For example, a nuclear blast can be described by a mathematical model that incorporates such variables as heat, velocity, and radioactive emissions. What is Schelling's segregation model? In 1971, the American economist Thomas Schelling created an agent-based model that might help explain why segregation is so difficult to combat. His model of segregation showed that even when individuals or agents didn't mind being surrounded or living by agents of different race, they would still choose to segregate themselves from others over time. Although the model is quite simple, it gives fascinating look at how individuals might self-segregate, even when they have no explicit desire to do so. Schelling's model will now be explained with some minor changes. Suppose there are two types of agents, X and O. The two types of agents might represent different races, ethnicity, economic status, etc. Two populations of two agent types are initially placed into random locations of neighborhood represented by a grid. After placing all the agents in the grid, each cell is either occupied by an agent or is empty as shown in the picture. Now, we must determine if each agent is satisfied with its current location. A satisfied agent is one that is surrounded by at least T% of agents that are like itself. This threshold T is one that will apply to all agents in the model, even though in reality, everyone might have a different threshold they are satisfied with. Note that the higher the threshold, the higher the likelihood the agents will not be satisfied with their current location. The picture above shows that a satisfied agent because 50% of X's neighbors are also X. The next is X is not satisfied because only 25% of its neighbors are X. Notice that in this example, empty cells are not counted when calculating similarities. When an agent is not satisfied, it can be moved to any vacant location in the grid. Any algorithm can be used to choose this new location. For example, a randomly selected cell may be chosen, or the agent could move to the nearest available location. In the image below, all dissatisfied agents have an asterisk next to them. The image on the right shows the new configurations after all dissatisfied agents have been moved to unoccupied cells at random. Note that the new configurations may cause some agents which were previously satisfied to become dissatisfied.
Context is crucial for understanding. To avoid context conflict, context problem by producing models, classical decision theory, and some agent-based simulation. Another way to avoid the context problem is to retreat into specificity of providing so much detail that the context is unique with no attempt. 3 ways forward are proposed. One is using data mining techniques to look for models whose output fits various targets kinds of behavior. Second is context-dependent simulation, modeling with the memory of the agent being context-sensitive and context-relevant knowledge and behaviors being applied in decision-making. And the last is number 3, combining qualitative and formal approaches, neither qualitative nor quantitative evidence being ignored.
E-science for politics and policies. Now, the digitalization of science, or some call e-science, the execution of scientific method through electronic means, consists of these fundamentals of science in the digitalization of both of them. So, we have the digitalization of empirical work that mainly refers to exploiting big data footprint on what has happened on the past and the usage of computer simulations that allows us to exploit what could happen in the future and combining both of them to pursue the holy grail of science, why it happened. And here are some examples on how computer simulations answer some very interesting questions in a setting of virtual reality. Let me give you one real-world example about the power of combination of analyzing big data footprint with computer simulation. One example who pioneered this modern technique was the Obama presidential campaign in 2012. What the campaign did was they invested $1 billion into a creation of 40 engineers, and they contracted these IT engineers from different companies like Twitter, Facebook, Craigslist, Google, and even some professional poker players. They created a group called Project Narwhal, where they created 16 million unique voter profiles in a process called data fusion, in which they use different sources like email sign-up, voter registration, volunteering records, and also tweets and FB postings, and also TV watching behaviors. Because they track 20 million set-up boxes. They rank 20% of the undecided voters on a persuasion scale of 0 to 10, and they ran 62,000 computer simulations to simulate voters' likely behavior during the upcoming presidential election. The value of this data pool led many uses. For example, the campaign paid 35% less than the opposing candidate on broadcast commercials alone. Also, they could tailor commercials to send to specific areas where this message will be better received than others. They could also predict the voters' outcome per state with an accuracy of 0.5%, meaning to say they could predict if they won the presidential elections before it even happens. Most impressively, they've changed the voting behaviors of almost 80% undecided voters only through Facebook. All models are wrong. Limits of science. Despite all the amazing achievements of modern science, there are fundamental limitations to the power of scientific method. The idea is that scientific methods are always models which are extracted from reality. They are like maps who describe reality, but they are not one-to-one. The basic question is that what is the largest map that could really be useful to describe reality? For example, if you are going to create a map that is 6 inches is equivalent to a mile in reality, that map itself is useful, but again, the model is wrong. If you are going to create a bigger map, it's gonna take a whole 1:1 ratio for it to be a useful map, or I mean a map that is right. Another example is if you have a digestive system, that model is wrong, since it's just an extraction from a reality. The reality of that humans have different kinds of systems in our body. If you can also see that using a human body, you can create another model, for example, a nervous system, which is an extraction from the whole reality, meaning to say that it is wrong.